Swayam Prabha. Digital India. Educated India.
Dear students, so today I will teach you some new topics and then we will try to complete this course slowly. So today just let's take one more tutorial and some new concept I will bring, and based on some discussions of the questions you can just try to remember all the stories and then try to make some new innovations for your thinking. I mean, you can make some new projects. So just think, today I will give you tutorial first that is very much useful for the various electrochemical sensors. So my plan today in this tutorial, I will discuss some important electrochemical equations and then you can apply those equations for applications of the sensors. Okay. So I already taught many electrochemistry. I already taught the characterization of the surface by the help of different like cyclic voltammetry, chronoamperometry, right? Cyclic voltammetry, chronoamperometry, chronocoulometry. Those all the electrochemical technique you have learned, and that is very much useful for biosensors, surface characterizations, detections, development of sensing device. But sometimes you may need to explain those cyclic voltammetry with some equations. So I just briefly, I will summarize few equations and you can use those equations for the explanations of the different signal outputs that you are getting, that you can explain. But let's I will cover a little bit our three equations. One is the Nernst equations, second is the Randles-Sevig equations, and third the Cottrell equations. Don't worry, they are not. I am not going to teach you all the mathematical details. Just try to understand how we can use those equations to predict the output that you are getting from the biosensor applications. So first, let's cover the Nernst equations. Before the Nernst equations, so I will try to explain you few things, very basic things. Just you can remember those basic things you already know. I think you already learned during your 10th class or 10 plus 2 class. That is the what is the anode, what is the cathode, that you know, right? What is the anode? So anode at which the where at this electrode oxidations happen, right? So if some ion, if M release one electron, if form M plus, it means oxidation. These oxidations happen if this electrode, that is called the anode. And the so the electrode that these electrodes actually, see, you know the biosensors, right? Your working electrode. Sometimes you are applying some positive potential, sometimes you are applying the negative potential. So those means sometimes there is maybe electro oxidations happen, right? Sometimes maybe electro reductions can happen. Means we are providing some electron. So you should have the basic concept. You already know, but before covering this Nernst equation, let's try to summarize. And what is the cathode? Cathode means at which the reductions occurs. So here means if M plus is takes one electron formed by M, then it become this is the reduction reactions, and at which electrode it happens, that is the cathode. So the electrode that the cations approach in this case, and electrode that anions approach, that is the anode case. So here is the schematic, the equations I plot here. Now let's come before covering the Nernst equation for Nernst that formula, you know already this. Please try to cover these slides also, that is the electrode potential, right. So, what is the electrode potential? So, potentials of an electrode for suppose some reactions happen, no, Fe3 plus, so it can take one electron from the Fe2 plus, or Fe2 plus can release one electron from the Fe3 plus. So, this kind of reactions or very common reactions like copper, you see here the copper 2 plus take 2 electron from the copper. So, this is in the cathode reactions, right, or zinc 2 plus takes the 2 electron from the zinc. So, in this case, I mean, if it is the opposite, I mean here when we are representing an equations, always we are mentioning the reduction reactions. But in a electrochemical cell, one part is the cathode, one part is the anode, right. So, one part you can see copper, another part is the zinc, right. I think you are very much well known about this setup. So, if one is the cathode and one is the anode, if zinc, this reaction is the anode, and copper, this is the cathode, right. So, in this case, what is the net potentials? So, that is called, this is the cell, right, one cell. So, in this cell, the E cell we say E cathode minus E anode. This is the net potential. So, the electrode potential are conventionally defined as the reductance potential like this, but actually reactions happen like zinc here oxidizing, copper here reducing, right. This is the actual cell. And E cell, I mean the net E, when electrode potential, net potential, I mean of the cell, E equals to E of the cathode minus E of the anode. Now, let us come to the representations slowly to the Nernst equations. When we are determining the potentials, right, in a cell, right, here you have a electrode, here anode and cathode and anode. So, you can remember I always told, means this potential, we are measuring the potentials of this cathode, potential of this anode, but you need one reference electrode, right. So, compared to the reference, based on this reference electrode, we can say how much the potential difference, that is the E of the cathode. The anode electrode, how much potential difference based compared to the reference electrode, that is the E of the anode, right. So, that is called the reference electrode. So, reference electrode always very much important. So, see, I am just summarizing all the concept here. So, I already taught you. So, we need always the reference electrode, because otherwise it is very difficult to understand the potentials of one single electrode, right. Generally, we are considering like silver chloride or hydrogen, standard hydrogen electrode, SHE, standard hydrogen electrode as the reference electrode, or calomel electrode, that is mercury based, they are the reference electrode. Generally, the standard hydrogen electrode, we are considering their potential is 0. So, 0 potential, and we can compare then here, I mean your copper electrode or your zinc electrode, their potential compared to the standard hydrogen electrode. So, they are the reference electrode. So, this is the very basic concept I already covered, just I am summarizing. Please try to remember and use this concept while you are developing a electrochemical cell. Okay. Now, let us come to the Nernst equation. So, Nernst equation, you can see these equations. I think you already learned these equations in your BSc, or who are already in UG course, maybe some of you already have learned in your 10+2 level also, but just I am just summarizing here what is the Nernst equations. See, the values of the E cathode can also be calculated in the other concentrations or activities. So, generally we are considering first the half cell reactions. What is the half cell reactions? Means the E of the cathode. So, this is the half cell reactions, whatever, suppose here reductions happen, or suppose here oxidations happen. So, this is the half cell reaction, this is the half cell reactions. that is E of the cathode or E of the anode. So, we can represent, suppose this is the reactions happening in the solutions. So, as I mentioned, generally we are representing the reactions as a reduction reactions. Reduction reaction. Okay. So, E electrode equals to E is equals to E0 minus RT by NF. Ln, say A R of R means this reductions, I mean this species by this species, and we are considering this activity of this all the species. So, where R is already the gas constants and F is the Faraday constants. Okay. So, E0, so what is, you can ask me, sir, what is the E0? So, actually E0 means actual potentials of your electrode, that I will come the next slide. So, we are calculating the actual potentials of these electrodes, that equal to E0 means actual formal potentials E0, that I am going to tell you again the what is the E0. So, E cell generally we are representing like this, E equals to cathode minus E equals to anode. So, how we can calculate the E equals to cathode, how we can calculate E equals to anode, that is the Nernst equations. From here we can calculate. So, you have to you should know the concentrations of your all the species. Here actually A means the activity, you know the activity equals to some factor equals and concentration. So, here we are representing all the your actual species concentration, you have to know, means activity. A means the activity, actual activity, you should have this information of your species, that is they are involved in the reaction. See, in this slide I just going to show you the E0 values, right, that I told you, no, that what is the E0. So, as I mentioned, E equals to E0 minus RT by NA, then all the activity of this species you have to mention here. So, what is the E0? E0 is the standard electrode potential. So, standard electrode potential is measured the electrode potential when all the species solutions or gas as an activity is the 1, and it is also called the standard reductions potentials, because we are representing the reductions way. And we are, see, if you go back the equations, here we are representing as the activity, and here is the equations like activity equals to some gamma x is the activity coefficients of his analyte or whatever. If a solute x, then you need one coefficient and the concentrations. So, that is you can calculate. So, standard electrode potential E0 mainly only we can get this one when your species in solution gas has an activity of 1, or that is in the ideal case, not always possible the 1. And all the formal potential, I just going to tell you the brief summary, and I mentioned here something that you can also try, you can also search. I already gave some reference book, please try to read the books also, so that you can understand if you want to learn more, then you can go through that book that I already put in the reference section. So, but all the parameter I already mentioned during the biosensor development, like what is the formal potential, you have to then try to remember the cyclic voltammetry, right. So, this is the cyclic voltammetry, suppose this is Fe2 plus form the Fe3 plus when it release one electron, then Fe3 plus form the Fe2 plus when it accept one electron, right. So, here is the oxidation. So, in this case is the oxidation and here is the reduction, right. Now, I already mentioned, right, this is the peak potential, this is the peak potential of the oxidation, reductions, and so if this is the E1 and if this is the E2, then we generally are calculating the formal potentials or E half value. E half value E1 plus E2 divided by 2 means this potential, right. So, this is actually formal potential that we can calculate from your cyclic voltammetry, Nernst equation case that I already showed you here, like actually your forward potential is 0 actual potential. In this case activity should be 1. You can see here measured electrode potential when all the species in the solution gas has an activity 1, then you get the standard electrode potential is 0. Please go through this few informations I already mentioned in the slide, but the main concept I already taught you last few classes, like what is the E half value, what is the forward potential, how we can calculate those things. Okay. So, this is the Nernst equations so that you can get the electrode potential value. Now, some other equations also can help you to predict your output that you are getting during the cyclic voltammetry measurement, during your amperometry measurement or coulometry measurement. So, another equation that I am going to tell you is the Randles-Sevig equations. What is this? Randles-Sevig equations, you can see this is just I am not going to derive, you just try to remember what is the relations between the different factors. No need to remember all the like value, just try to remember the relations of the different factors. Suppose you got one cyclic voltammetry, something like this, means you are getting cyclic, when you are getting cyclic voltammetry. So, you are scanning within a potential window and you are getting current, right, and within this potential window. But there is so many other factors also can affect in this cyclic voltammogram, like your current can be changed, your this E half also value also can be changed. There is some different factors. See, one factor is the concentration. What is concentration means? What concentration? Concentrations of your the redox couple you are using. Suppose you are using Fe3 plus Fe2 plus, right? This redox couple you are using. So, if you increase the concentrations of iron species, then definitely you will get the higher and higher current. If you increase, then you will get higher current. Again increase, you will get the higher current. So, this is depend on the concentrations. More concentrations, when you will get the more current. Not only the concentration, there is another factor can affect, that is the scan rate. I mean, how fast you are scanning within this potential window and you are getting the this cyclic voltammogram. No? So, suppose you have the Fe3 plus Fe2 plus, right, this one in the solutions, but if you scan, when I will show you during our laboratory means demonstrations, I will take some laboratory demonstration, that time I will show you in the instruments, that is called a potentiostat. In this instrument, if you apply slow scan rate to high scan rate during the cyclic voltammetry measurement, your current, high scan rate, your current also will be increased, because your this species can move very fast towards the surface. It means your current means IP, that is why I am going to say that IP means your current, your maximum currents that you are getting, that IP is proportional to actually your scan rate, how fast you are measuring this cyclic voltammetry. Means some are measuring slow, some are measuring fast. So, that is why when you are going to publish your work, you have to mention which scan rate you are using. That is the relations, IP and the relation is the proportional to scan rate to the power half, means it is saying is a root, there is relations. Okay. So, if you increase the scan rate, and accordingly you will their current of your cyclic voltammeter also will increase. So, this is the relations, no need to remember, just try to you can correlate or you can explain your output data based on the scan rate. That is the main my goal, to tell you the Randles-Sevig equation. So, while you are developing the biosensor surface, sometimes you may scan fast or sometimes you may scan slow, and you are getting different current, that you can explain it because of this relationship. That is my main motive to tell you these equations, and all the factors, like this is the number of the electrons in this how many number of electrons is flowing, like Fe3 plus, Fe2 plus, here number of the electron is the 1, because now only 1 electron. So 3 plus 2 plus is reducing, 1 electron is taking, right. So here n equals to 1, and A is the electrode surface area. So see, this electrode surface area also is very much affecting on your current. So suppose your working area A1, and if working area increase to A2, definitely you will get the very much high current because of the high surface area. Because the higher surface area you will get the higher current. So your current is very much dependent on the surface area also. So here two very important things I am just telling you, or you can explain your output of your cyclic volt thermogram, that is it will affect, one is the scan rate, another is the surface area, and another thing the diffusion coefficient D the diffusion coefficient, that depends on in your, I mean which solutions you are using, based on your redox couple. So different redox couple in the solution, they have the different diffusion coefficient. Okay, so if you fix like same solution, in this case the diffusion coefficient is constant, and if you fix the area of the electrode and working electrode, then your area also constant, but if you increase the scan rate, then you will get the higher and higher current, right. So this is the one important information for you while you are, when you will characterize the biosensor surface. So you can try. Okay, next thing is the Cottrell equation. This is again the very simple things. I don't want to derive the equations, that I want to tell you. The Cottrell equations actually is describe the change in electric current with respect to time. Suppose you are measuring the different chronoamperometry, right. So here you are applying a fixed potential and you are getting the output of the current. So current with respect to time that you are calculating or you are measuring by the help of chronoamperometry, so there can be some effect, change of current can happen with respect to time, and that you can explain with the help of Cottrell equation. So this is the Cottrell equations. What is this? So that Cottrell actually is describe, this one basically describe the current response when potentials we are applying in a measurement. The current measured depends the rate that the analyte diffuses to the electrode, and current. Suppose see, you have the electrode surface and some analyte actually diffusing, right, to the solution, to your electrode. So from bulk solution through bulk solution towards the electrode surface. Okay. So when material diffusing from bulk to electrode surface, so there is different parameter, different conditions can affect your current with respect to time. Means generally we are expecting what, like with respect to time you are measuring current in the chronoamperometry. So this current will be always constant, but sometime maybe there is some different diffusion. So that is called diffusion control. Means if your analyte, that analyte is diffusing towards the surface, so somehow its effect, then you will get the different, maybe with respect to time your current also can be changed. So that things actually written here, the how the current can be changed, what is the factor. So I is the current, and n is the, as I said, the n is the number of the electrons, f is the Faraday constant, a is the area of the surface, and C0 here, that is initial concentration of the reducible analyte, and D the diffusion, and T the time. So this is the relations, and from here you can think about the change. If there is any problems of the current change, that you can explain with this equation. One important thing that I am going to tell you here in the Cottrell equation, like is a planar, sometimes it can be different surface. See, it can be like, see this line, the Cottrell equation describes the case for an electrode that is planar, but it also can be derived from a spherical, cylindrical, rectangular geometry means if your surface is different or there is some different kind of reactions happen, that everything can be explained through these reactions, and there is a possibility of change of the current. I think one thing I just want to mention to you very clearly, when as we are at the end of this course, when we are getting different current or charge or different shape of the cyclic voltammetry, definitely you have to explain properly. And for these explanations, you can use these three equations. So, one is the Nernst equation you can use. From here you can measure the potentials. Also, you should have the information of the formal potential. So, this information sometimes you can include while you are writing a manuscript. You should have this information, or based on this information you can predict some uncertainty, or if there is any problem on your biosensor surface, that also you can predict. And this Reynolds-Savage equation that I just mentioned, this is very simple, like just changing the scan rate and how your measurement can be affected, right? And then Cottrell equation, this is mainly telling you that the current can be changed with respect to time with these equations, and so many uncertainty if they happen that you can predict. So, mainly I wanted to mention here in this tutorial, this is just few equations I just described. One is Nernst, Reynolds and Cottrell. Not only these three equations, you can think some your independent way, and you can try to explain some different factors. As I told, some many uncertainty can happen during the fabrications of your biosensors, and you have to think, you have to explain why you are getting different shape, why you are maybe you are not getting an expected result, why you are not getting that. You can explain by existing equation, or you can model something new also. With the help of your, if you have some computational knowledge, you can try some simulations, then you can develop some new equations also. That is my main motive for this tutorial. See, as I mentioned, suppose like chronoamperometry, right? Let's explain this. I can ask you this question, right? Why at the very beginning it is very high current you are getting, right? Current versus time when you are measuring chronoamperometry. At the beginning you are getting the very high current, then slowly it is coming to that where equilibrium form. Why? That you can explain because your electrode surface you are using suppose Fe2 plus. So at the very beginning your surface very near to the surface. So electrochemistry mainly here is the surface reactions, right? It is the surface reaction. So at the near surface you have lots of Fe2 plus, right? And here you are applying oxidation potential. So Fe2 become the Fe3 plus, right? One electron it will release Fe3 plus. Because at the very beginning you have lots of Fe2 plus, that's why you are getting very high current. Now Fe2 plus Fe3 plus means that slowly the Fe3 plus concentration will increase, and in the near surface not only the Fe2 plus, there will be the Fe3 plus also. That's why your current will be slowly decrease, because the concentration of Fe2 plus the very near surface will decrease. Then slowly there will be equilibrium of the Fe2 plus and Fe3 plus, and you will get the equilibrium current. Like this way you can explain. So this is the like Fe2 plus is diffusing towards the surface, and then Fe3 plus form, then again it will come to the far from the surface, then slowly there will be equilibrium. Like this way you can explain. So this is called a diffusion effect, mass transfer effect, and how mass is transferring towards the electrode, that also you can explain. And the shape, see, like shape of the cyclic voltammeter, if this oxidation peak, reduction peak, they are very close, means it is kind of the what? It is a reversible. Your reaction, if it is reversible, then your oxidation peak and reduction peak will be very close, because they can easily oxidize, easily reduce, right? Means Fe3 plus goes to Fe2 plus easy, and then Fe2 plus to Fe3 plus, it is also very easier. So you will get the very good shape. But if the oxidation reduction peak is very far, right, like this, like here oxidation, here reductions, means in this case it is kind of irreversible process. In that case they will go very far from each other. So like this way you can explain also many things. So you can characterize your biosensor surface. Mainly if your sensor surface electron transfer rate is very fast, easily electron can transfer, then you will get very reversible phenomena. But if there is a hindrance of the electron transfer, then you will get the irreversible phenomena. Okay. So like this way, just try to explain your all the data. The next class again I will show you some other important topic, some based on my tutorial lecture, and then slowly I will complete all the descriptions of this course. So please try to read this reference book that I mentioned, no, the Cottrell equation, Randles-Sevicki equation, Nast equation, that is very much well written in this book. That is electrochemical methods, fundamentals and applications by Ellen J. Barr and R. Faulkner. This is the second edition book. Please try to remember and try to read this book also. So that's all for today's this tutorial, and next tutorial I will cover some basic biosensor part, so that you can remember all the things that I taught in this class. Okay, thank you very much.